Hello guys, welcome to our presentation. We are group science guys, and today we're gonna introduce you the elastic and plastic deformation. So let me just introduce to you first our group members. My name is Hassan and Colin and Konal. So today, at the end of this lecture, we're gonna have like a little bit understanding of the elastic deformation and plastic deformation. At the end, we're gonna do the tensile test example. So let's start with our introduction. Often materials are subject to force loads when they are used. Mechanical engineers calculate those forces, and material sciences how materials form, elongate, compress, and twist, or break as a function of applied load, time, temperature, and other conditions. Material sciences learn about those mechanical properties by testing materials. Result for the testing depends on the size and the shape of the material to be tested, how it is held, and the way of performing the test. This is why we use common procedures or standards, which are published by American Society for Testing and Materials, which is known as ASTM. Elasticity and plasticity are used to find the strengths of material to be used in various applications. So let's start with elastic deformation, which is defined as a temporary shape change that's self-recovering after the force is removed, so that the object returns to its original shape. So in the other words, we could say it is the change in the shape of the material at low stress that is recoverable after the stress is removed. Elastic deformation can be caused by applying shear forces or compressed stress. In contrast, plastic deformation occurs when these stresses are significant, be permanently deform the metal. In plastic deformation, breaking of bonds is caused by the dislocation of the atoms. So we have an example of like the elastic deformation. You see that shape when it's elast, and that's the graph of it, which should be linear. And other image which we have, that's a ball like hitting the wall, like as you see in the image, and then it will just like return back. It's kind of like the original shape. And that's a graph of the stress strain, which is shows us the elastic region, elastic limit, and then after that there is a point when it's come to the to form like the plastic region.
Hello, I'm Colin. I'm here to talk about plastic deformation. So plastic deformation is when material doesn't return to its original shape, and it's caused by microscopic dislocations, like this image shown. The atoms are changed, so it cannot recover. Engineering stress is force over the original cross-sectional area, and engineering strain is the change in length over the original length. In this graph, the red line shows the engineering stress strain curve, and the blue line is the true stress strain curve. The difference between these two curves is made because the Poisson's effect, where the area decreases while the length increases in the material. Yield strength is when noticeable plastic deformation has occurred, and it's right after the elastic deformation up top. In this graph, we have ultimate strength, which is on the maximum stress of this material, and at fracture strength. Ductility is a measurement of metal's ability to withstand tensile stress. So the more ductile it is, the pointier the breaking point is. This is just an example of the plastic deformation. Hardness is the ability of material to resist denting from impact, and it can be tested in different methods. These are some of them. Toughness is the ability of material to absorb energy and plastically deform without fracturing, and it's approximately under the area under the stress strain curve.
Hey guys, this is Kunal here. Today we're going to talk about some examples of elastic and plastic deformation. So let's get started. This is the tensile strength machine. So basically, metal specimen or the testing specimen is clamped on both the ends, and it's been pulled on the opposite directions. And all the data has been taken, like how much load has been applied and what's the elongation point at any given time. And with that, we get a graph like something like this. So that's on the y-axis it's stress, and on the x-axis it's strain. So basically now here we got a elastic deformation example. So in this example we got a cylindrical steel alloy specimen, which is 18 mm in diameter and 85 mm in length. It's been pulled in a tension force. To find the elongation, first we need to find stress at 30,000 newtons. So let's get started with it. So as you know, stress formula is force upon area, the cross sectional area. So when we check in the values in this equation, we get 117.5 megapascals. After we get the stress, we plot stress on the x and y axis of stress and strain curve. We get strain about 0.008. 0.008. Then this is the formula for strain. Then to get the elongation, we rearrange the formula, and then we put in the values. We get 0.68 millimeters. That's the elongation for our specimen. And let's go to the next example now. So this is plastic deformation. So plastic deformation example, its first question it's asking what's the modulus elasticity. So here's our graph, and here it asks what's the modulus of elasticity. So we plot around 100 degree 100 newtons, 100 megapascal of stress, and strain is nearly about 0.003. After putting the values in the formula of slope, which is basically difference of stress over strain, difference of strain, we get 33.33 gigapascals. Our next question is what's the proportional limit. So proportional limit is where the linearity of the graph ends. So you can see here it's the proportional limit of proportionality. So let's get see our question here. So if the line goes straight here, but then somewhere near the 200 megapascal it ends and it starts to curve ahead. So that's the point where is our proportionality limits Okay, so next question is now again, what's the yield strength at strain offset of 0.005? So yields, we take the 0.005 point and we start plotting it towards the yield strength on the stress and strain curve. And once we get a point in on the curve, we take it back to the uh, stress, and we get the answer is about 230 megapascals. Now our next question is, what's the yield strength? Yield strength is like what amount of load any specimen can handle before breaking it. So that's the tensile strength, which goes as the maximum amount of force, the stress it can manage any time on the any given time is this one. And when we put it back on the y-axis, we got about 1990 megapascal. So that's the stress and strain curve. It just wraps up the all we talked about now. The first one's proportional limit, the next one was the elastic limit. Now we get upper yield point, and after which we get lower yield point. And then we get the ultimate load point, which is also called the ultimate tensile strength of the specimen. And the breaking point is our fracture point. With this video, I hope you guys have better understanding of elastic and plastic deformation and why it's so important to know its mechanical properties of any specimen before its application in any engineering world, rather it be civil engineering, civil application, or the mechanical engineering for machine that picks up the weights. It's better to know beforehand. And I want to thank you for watching, and have a nice day.